Hi everyone, welcome to part 3. This is the third and final part of section 4.4. So we are almost done with chapter 4. In this video, we just want to look at these last two bullet points. In our previous video, we ended off by looking at the relationship between the exponential and the Poisson process. So in this video, we want to finish off looking at the exponential by looking at what is called the memoryless property as well as its proof. And then we will look at the exponential at the very end. Okay, so if we let x denote the lifetime of something, where x follows an exponential distribution parameter lambda, then this probability holds. All right, it's given on page 199. This property here, this whole equation, is what is referred to as the memoryless property, or sometimes it's also referred to as the property of no memory. Now, it looks like a lot of maths, but what I want to do now is just, with an example, just help you understand what this equation is telling us. So let's consider this hypothetical situation. Suppose at some point in time I bought a car. All right, so let's say I bought a Lambo. It's a red Lambo because I like red cars. And let's say for the purposes of this example that the probability of x greater than or equal to 10 is equal to 0.9. So let's work with years. So what this is telling me is, remember, x is lifetime, all right? So in other words, how long this car is running for. So the probability that this car is still running for at for 10 years or more is equal to 0.9. So this car has a 90% chance of surviving more than 10 years. All right. So let's say I drive this car and you know that, okay, it's still running, after a year. So the car is still functioning fine. The question I want to ask you is, what is the probability that this car will survive another 10 years? All right. So in other words, given that the car has been running for at least 1 year, what is the probability it will run for at least 10 more years? And this probability is actually what is represented on the left side of this equation symbolically. So given that the lifetime is at least t0, so in my example, t0 is 1 year, what is the probability that the lifetime will be t plus t0? So that's your t, and then add an additional t years onto that. Okay? So let's look at how this would then be applied. So we're saying here that given that my car survived 1 year, what's the probability of it surviving 10 plus 1? All right? So in place of t0, I've put 1, so 1, 1. In place of t, that's where I've put 10. So you could have also written it this way. Given that my car has been running for at least 1 year, what's the probability of it running for at least 11 years? Okay, so that's an additional 10 years on that 1 year. And according to the memoryless property, we can immediately see that this probability is the probability of x greater than or equal to t. All right, and we said t is 10 years. So that's x greater than or equal to t. And at the beginning of this example, I said let's assume that probability is equal to 0.9. So in other words, the chance of my car surviving another 10 years, given it's been running for 1 year, is 90%. All right, let's try another example. So what if I have been driving my Lambo for 10 years? All right, what's the probability of it surviving another 10 years. So we're going to follow the same procedure. So I've changed t0 and we're keeping t the same. And all that changes now is where we have our t0. So that's your t0 and that's t0. And this is just my t. It remains the same. And according to the memoryless property, this thing which we have is equal to probability of x greater than or equal to t. And in this case, t is still 10. So that means x that's equal to 0, 0,9 or 90%. So in other words, if you know that my car's been running for at least 10 years, the chance of it running another 10 years is 90%. Okay, let's do one more example to drive this point home. So let's say this car, it's a ninja car after 100 years. Okay, it's like a fossil, but it's still running. After 100 years, it's still running. And what is the probability that it will last another 10 years? So that means it's going to get to 110 years. Let's do the same calculation. All right. So in this case, T0 has changed, but T hasn't changed. So you can see I reflected that in my formula. And because it's exponentially distributed, we can use the memoryless property again. And surprise, surprise, what? The answer is 90% again. So, yeah, you are probably scratching your head thinking, no, this doesn't make sense. There's no way that, a car that's 1 year old um, can last for another 10 years with 90%, and then it's also 10 years, also probability of 90%, and then it's 100, and then it's still 90% chance of running. So in this, but this is what the memoryless property is telling us. So it doesn't actually make a lot of sense. So I think the take home from this example is the exponential, it's not going to make sense in every single scenario, but there actually are some cases. Okay, so let's just move on a little bit now and let's now look at in general. I hope you're already starting to see why this is called the memoryless property or the property of no memory. You see what this exponential distribution did? It completely ignored the fact that that car was running for, was it 1 year or 10 or 100 years? It completely ignored that and then concluded that the probability of the car running an additional t years was the same regardless. Like, come now. I'm sure you're thinking, but why would you want to use this property? I'll come to a few examples just now. So, more formally, you'll find the statement in the textbook. It says the length of time a component, so it could be a part of a machine, not necessarily a car. So the length of time a component has already operated does not affect its chance of operating for at least t additional time units. Put differently, this memoryless property completely ignores the effect of wear and tear. So the distribution of the remaining lifetime is independent of the current age. So hopefully you can see from the previous example, it probably isn't a good idea to use an exponential distribution for the lifetime of a car because there's definitely wear and tear. It matters if a car is 10 years old or 100 or 1,000 years old. So you might want to use maybe a gamma distribution or other distributions that we're not going to cover here because they don't have the memoryless property. But there are scenarios where you might actually have things that um, follow that make sense to have that property. So an example would be the lifetime of electronic components such as fuses. So it doesn't matter whether the fuse has been there for a year or 1,000 years or not. The probability of surviving an additional t years or months or minutes remains the same. And an interesting fact, the geometric distribution is another distribution that also has this memoryless property. Okay, so now you understand, hopefully, what the memoryless property means. Let's prove it. So, in order to prove that this statement is true for the exponential, we need to show that the left-hand side is equal to the right-hand side. So we're going to start off with the left, and then we're going to furnish all the steps that are hidden there and end on this side. So on the left-hand side, we're just going to copy the equation as given. The first thing that we're going to do is we're going to use the definition of conditional probability. So if you remember, the probability of A given B is this probability. So my A is this, and this is my B. So if I put it in this form, I end up with this intersection that divided by that. All right. So let's focus on the numerator. If I draw myself a number line, so if I have a value t0 and then I add t units, you'll end up with t0 plus t. Okay, so if we focus on the different parts, this part and that part, I can draw them quite nicely here. So everything from t0 onwards, that's where you have your probability of x greater than or equal to t0, and everything there is for the other side. Now, if we want the probability of the intersection now, we can actually simplify this by focusing on only the intersection. So the only place where both of these two things occur is on this region onwards. So in other words, from here to there where I've just added that arrow. So you can simplify the numerator by just writing it as x greater than or equal to t plus t0 because that's where the intersection is. Okay. All right, so from here now, let us bring in that exponential distribution. So this is the CDF that we derived, and it's 1 minus e to the power of minus lambda x. Okay, I would like to go straight to using the greater than or equal to version instead of the less than or equal to. It's just a bit easier that way around. So let's work it out. So if I wanted x greater than or equal to x, then I'd have 1 minus that CDF. And then if I substitute my fx, it gives me this line, and this simplifies to e to the power of minus lambda x. All right, so now I have this probability equals e to the power of minus lambda x. So now that I have this expression for x greater than or equal to some value, I can apply it directly here. So instead of x, I have t plus t0. So I can replace the numerator with this e to the power of minus lambda, and then in brackets t plus t0, and I'll do the same thing for the denominator. Now I can cancel out the e to the minus lambda t0, so just simplify this, okay? And you will end up with e to the power of minus lambda t. Now, if you compare this with that, they actually look the same, but it's just that x is replaced with a t. So what that tells us is this is equal to the probability that x is greater than or equal to t. And this is exactly the right-hand side of our equation. So that completes the proof. Let's end off the exponential distribution section with an example. Have a look at this example, pause the video, and see if you can apply the memoryless property in this scenario, and then we'll look at the answer just now. Okay, I hope that you pause the video and attempted this question on your own. The answer that you should have gotten is 0,60653. And if you got that answer, well done. Congratulations, you did really well. And let's have a look at the working out for this. The question says, suppose that the amount of time one spends in a bank is exponentially distributed. So let's start off by just copying the random variable from that statement. X is the amount of time spent in the bank. And then the second step we're going to follow is we're going to identify the distribution and the parameter. So fortunately, the distribution is given in this case, so we know it's exponential, but what is the parameter? So we are told that the mean is 10 minutes, okay? So our parameter is actually 1 over lambda, but we're given mu. So you need to make an equation and then you solve for lambda. So just watch out for this. Like a lot of questions will give you the parameter, the mean, and then some students will go and use that value as your parameter, but the mean is not the parameter for the exponential. Okay? It's 1 over lambda, so therefore you solve for lambda. All right. So the question now says, use the memoryless property to calculate the probability that a customer will spend more than 15 minutes in the bank, given that he is still in the bank after 10 minutes. So this is immediately, hopefully you can see from that glaring word, given, a conditional probability. So you know that this person has been there for at least 10 minutes. Now it's saying what's the probability there that they'll spend more than 15 minutes. So in other words, given that this person has been there at least 10 minutes, what's the probability of being there at least 15 minutes? Okay, so you've been there for 10, so they're staying an additional 5. Um, if you compare it with this memoryless property, which is something you need to memorize, it's not given in your formula sheet. This on your right is x greater than or equal to t0. So immediately you know what your t0 is, which is 10. And then from that, you can figure out that if this thing is equal to 15 and t0 is 10, that means t is equal to 5. So like I said earlier, you've been there for 10 minutes, and then you have an additional 5 minutes to make it that 15. And then the memoryless property tells us that this probability is equal to x greater than or equal to t. So we've identified from here that our t is 5. So you can straight away go and write x probability of x greater than or equal to 5. And then from there, you know x follows an exponential distribution with these parameters. Okay? So you can integrate from 5 to infinity over this PDF with parameter 0.1 in place of the lambdas. And then that is how you'll end up with this final answer. So that brings us to the end of our exponential distribution section. Now let's just quickly look at the chi-squared distribution. So we are now looking at this last bullet point here. We've done the first one, and this is a nice short section. There's no calculations. It's just to make you aware of why the chi-squared is so important. Similar to the exponential distribution, the chi-squared distribution is a special case of the gamma distribution, specifically the case where alpha is equal to nu over 2 and beta is equal to 2, where nu is an integer greater than 0. So that symbol is just a Greek letter, nu, and what they're saying here is that if you have this choice of alpha and beta under this condition, then the result is something like this. So the shorthand for a chi-squared is this curvy x squared, and then you only have one parameter. And similar to the other case where we had lambda and alpha is fixed, here beta is fixed to be equal to 2, and then we have freedom to choose what value of nu we want as long as it satisfies that condition. So overall, we're saying that if we have a gamma with these parameters, then it's equivalent to a chi-squared distribution with parameter nu. And the parameter for a chi-squared distribution is similar, has a special name. It's called the degrees of freedom, and that's something you will look at later in one of the later chapters. But for now, just know that's the special name. So if you take the PDF of a gamma distribution and you substitute these parameters in place of alpha and beta, you will end up with this result. And then if you simplify everything, you end up with this. This is just your chi-square distribution with new degrees of freedom. So why is this so important? Well, it turns out this chi-square distribution, it forms the basis of a lot of the other procedures that you're going to cover in later chapters. And it's been introduced here not because you need to use it, but because of its relationship to the gamma distribution. So it's just something they want you to be aware of. So just like other distributions, you can find probabilities, but this is one of those complex cases. So there are chi-squared tables, which will teach you how to use next semester. And you also have your moment generating function. And it's pretty much just the same procedure. The way you handle continuous random variables and their PDFs, you do the same thing for any distribution you're given. So don't get confused when you get new distributions. It's pretty much the same maths. You integrate, you differentiate, etc. So an example of where this distribution becomes relevant is as follows. So before I give you the example, I just want to give you a quick reminder. So remember how when you have x that is normal with parameters mu and sigma squared, if you transformed x, it gave you a different distribution. So specifically, if you take x minus mu over sigma, this gives you a standard normal, a normal 0, 1. So similarly, if you take z, which is a standard normal, and this time your transformation is taking the square of z, then you end up with a chi-squared 1. So this is actually just a nice, interesting connection. You don't need to prove it at this stage. You'll see it again in later chapters. So this brings us to the end of chapter 4. I hope you enjoyed it. I enjoyed teaching you. So please don't hesitate to get in touch with me or the tutors if you need any assistance. Wish you all the best.